All right, go ahead.
Okay, today I will represent the article about phase transitions in large language models and the uh, O of N model. Uh, this article was written by Youran San and Babak uh, Haghighat. Okay, sorry. And we will discuss the architecture of transformers that underlies on this large language model. Uh, this will discuss the POTS models and how we can uh, how we can um, you how we can unite transformers and Wolfram model, and so we'll discuss the result of experiments. Okay, um, the article is devoted to the study of phase transition in large language model and their connection with physical models. Um, the authors propose to reformulate the transformer architecture as O-fan model, which allows it to be analyzed from point of view of the physical or phase transitions and critical phenomena. Um, let's start to discuss transformers architecture. So the first step is tokenization. For machine to understand human language, we have to transform a sentence into numbers. Simply speaking, a token is a subword. So we can, uh, for sentence S, the tokenizer splits into tokens. Uh, this picture is demonstrate how it looks. Uh, for example, and T is the token, and L is the number of tokens in the sentence. The next step of this architecture is token embedding. Each token is mapped into a vector space where n is embedding dimension. This can be represented as matrix E, where each row corresponds to the vector of a token. So uh, big V is a vocabulary size, and N is the embedding dimension. After tokenization and embedding, the sentence S is transformed into a list of vectors. So, whereas T right now is a vector representation of token, and on on this picture you can see the example how it's going. And the second step is applying of attention layers. The attention mechanism computes queries, keys, and values for each token using linear transformations. So we can represent this process by such equations. And how it works. For example, we can focus on the last token in the sequence and first compute the dot product between the uh, query and all keys. The dot products are treated as energies. To convert these energies into probabilities, we use the Boltzmann distribution, softmax, at a temperature beta. And beta is inverse temperature, what we will discuss uh, further. So, the results of applying attention to last token is the weighted sum of the values V, whereas the weights are the probabilities from Boltzmann distribution. And we can describe in this scheme. So if we consider all queries, the attention mechanism can be written like this. We just generalize this equation and uh, have and get this form. So Q, K, and V is the matrix of our values. And the second step is after applying the attention mechanism, each token, which was originally a vector in our surface, is mapped to a new vector in this surface. So after that, a linear layer, feed-forward neural network with activation function is applied to each token independently. And the computation of the transformers layer can be formally written as this form, where M is the number of transformers layers, so and FF the feedforward layer, and our attention mechanism, what we have discussed previously. So the output of the transformer corresponding to the last token after another linear layer is explained as the probability distribution of the next token. Okay, and the next part, uh, there is POTS and O of N models. The POTS models is the generalization of Ising models. It consists N plus 1 spin states on each lattice side with the nearest neighbor interaction depending on whether two neighboring states are the same or different. The spin states can be represented by n plus 1 vector E, um, and I we associate with internal degrees of freedom. The vector satisfies the orthogonality condition that you can see. If we have equal vectors, we will get the one. And the partition function of this model can be presented in such form with external source, of course. And whereas sigma and t denote lattice sites, t are the spin variables at site sigma taking values from the unit vectors E. And big K is a coupling matrix, which is symmetric and non-zero only for nearest neighbor sites. And usually we can represent the POTS model and such type of model and field theory representation. And to derive a field theory, the following identity is used. So type of equation, and whereas phi is a new field variable with n components for each lattice site. So in continuum limit, the field phi is replaced by a continuous field phi of x. To this end, one performs the sum over the spin states T. The term is expanded in local derivatives of phi, and higher order terms are discarded. This leads to the equivalent Hamiltonian that has such form. And authors consider restricted pods model, and it means um, they don't consider this I don't see this member of our equation, and this model includes two and two multiply n plus one state vectors plus and minus e. And for such type of model, we can represent our field theory action. And it's interesting that for the more than four dimensions, the interaction term is irrelevant, and the theory is expected to flow to free theory in the infrared. However, in six dimensions, interacting ultraviolet fixed points exist, and is shown in phase article. And this fixed point is unitary only for n more than 1038, leading to an interacting conformal field theory. Um, in Matty's article, the critical exponents for such ultraviolet fixed points is higher dimension were computed, and it was found that for um, it was found that for infinity n, we can get some equation for critical exponent related to the correlation length. And correlation length scales near the critical temperature uh, can be expressed like this system. So um, in the one of n model, interaction are local, meaning only neighboring spins interact. In the attention mechanism, interaction are non-local. Any two tokens can interact. However, for given token, the attention strengths with other tokens vary. We can extract the dominant interaction and treat the rest as perturbations. Those perturbations don't affect critical phenomena, as critical phenomena are rigid. For example, the expectation value of the square of the dot product of two random unit vectors in n-dimensional space is expressed by this formula. But we can use such type as the threshold for dominant interaction. So, how it works? Based on this threshold, we construct a graph where nodes represent tokens and H represents strong interaction between tokens. This graph can be embedded into a high-dimensional space where interaction between tokens become local, nearest neighbor, and the dimensionality of this space is called the internal dimension and is denoted by D. The internal dimension reflects the complexity of the system. The higher D is more complex system. And for our system, we can get the energy according to this equation. And I remember L is the number of tokens, and C is a vector representation of token. And we expected the specific heat near the critical point to have this behavior. And so from this form, we can express the equation for temperature behaves. And it looks like this. Whereas alpha is our critical exponents, what we will discuss.
Can I ask a question? So I understand how they want to represent the tokens with spins and use this analogy of the ON POTS model, but why are we expecting the system will be in a critical state? So why? I mean, surely there will be interactions between those tokens, and maybe they'll be described by some probability distribution. But why do we think that the system will be? Now, I agree it will be critical, but do they say why they think it will be critical? And
In introduction, the authors discuss that this type of model, large language model, has a critical values, and they also have represent some results from other authors, and
Mhm.
I I don't include in my main part of presentation, but I left it.
Sure.
I have left it for
So
extra
you're saying
case.
that's just empirical result that shows that the system behaves critically. I don't know, but for that they have to calculate some kind of correlation function. I don't know what, but or how the energy behaves as a function of temperature. So okay, so fine. And the second question I have, like when you were presenting the POTS model, ON model, you've been using the same number n for the number of lattice sites and for
Give me a
dimensionality
second.
of those spins. Now way before. So yeah, here.
This part.
Right. So
Okay.
there's n plus one spins, and each of them is an n-dimensional vector. Now with transformers, those are two different numbers, right? So there is L, which is the number of tokens, and they're like spins, and each of them is embedded in a high dimensional space. So the dimensionality of the embedding space is this, the second n. So they're n and L. There are two different numbers, and somehow here they are putting it to be the same. Is this a typo, or is this what they really want? Because certainly for the transformers there'll be different numbers. The one will parameterize the spins, and the other will parameterize the dimension, the components of each spin. Right? Maybe it's just a typo. I don't know.
Okay. Maybe it helps to answer your question. The uh, demonstration of reform rate transformers. Um, so
No, I understand it's going to be ON. I mean, I understand how you can model it as an ON model, but I just don't think the number of spins will be equal to N. The number of tokens is a different parameter, so I wouldn't. It's not the same N. It's okay. It may just be a typo. No worries. But the other interesting aspect that you said is that the perturbation theory approach. You basically in this graph you're just drawing edges between the spins or these tokens that are strongly interacting. Yes, and then
yes, yes.
okay, but then at some point you said you only consider one strongest interaction. So I would assume that then each vertex will be just connected to one other vertex. So maybe not the strongest, but there will be some kind of cutoff, and you will only draw the edges to the other tokens which for which you have strong interactions, but not necessarily, it wouldn't be only a single edge, right, for each vertex. Otherwise, it would be a very boring graph.
Okay. For this point, the author have noticed that the strong interaction, what they introduced, it does not affect on results, to be honest.
Mm-hmm. Okay.
And we can discuss at the end, maybe.
Maybe last final point. So you have those tokens interacting through the attention layer, but then you go through this layer many, many times. So it's like kind of you have a flow of models of the interacting tokens as you pass through one attention layer to another attention layer to another attention layer. So presumably the whole theory is also has experiencing some kind of flow. Are they talking about that flow anywhere?
No,
Okay,
I didn't talk.
okay, that's fine. Sorry, I ran out of the questions, but I had many. Sorry, go ahead.
Okay. And okay, is now when results for some critical values, critical exponent, and they use this equation, and from this relation they expressed alpha, uh, the critical exponent, what we interesting in this work, and they uh, uh, they have got this relation for alpha and d, our internal dimension. And this method of estimating D is independent of the initial definition of the internal dimension, and it doesn't require specifying which interaction should be ignored and which should be kept. The dimensionality can be determined solely from relationship between energy and temperature.
So I'm lost
Um,
here. So what is the internal dimension? Dimension in which you can embed the graph. No, that was the definition of the internal dimension. Before you gave a definition of internal dimension, I thought it was dimension at which you can embed this interacting graph. If you go up, I think there was some place you said in. Yeah,
uh, yes. This graph. Uh,
but
what
that's
we
again,
have
it's an
here.
arbitrary number. I mean, you change your threshold, and then it will be a different dimension. It's not the number that is fixed by the problem.
Okay,
As you
maybe.
change the threshold, you'll have the dimensionality will be higher and higher. I guess it has to be defined more precisely someplace, but that's okay.
Okay.
Go ahead. Sorry.
Um, no, thank you. Um, and okay, now we can discuss the results, and the first graph represents the dependencies between energy and temperature, and of course this theory was tested on the Quen model series, and so from small to large parameter size, from 0.5 to 32 billion parameters, and the text from the English Wikipedia was used as initial hints, and the models was allowed to freely generate 1024 tokens at different temperatures T. And what we can see, all models exhibit a phase transition at temperature equals 1.2. Um, and when temperature less than critical temperature. The model generates meaningful text, and where temperature is more than critical temperature, the text becomes meaningless, nonsense phase. And this part, it's not so, maybe it's not so understand right now. You can't understand this right now, but the last experiment of authors can explain to what these results means. So, small models exhibit negative specific heat in the nonsense phase, and this be explained by the fact that the models continue to generate text with low energy, indicating that they are not aware that they are generating meaningless text. And large model behavior similar to the second order of phase transition observed in the Ising model. Uh, in the nonsense phase, large models generate text with high energy, indicating they are aware that they are generating meaningless text.
So the temperature is the
So,
parameter that you supply to the model, probably related to this beta that you had. But what is energy? How do you measure energy there?
yes, energy measured according to this relation.
Yeah, but not just this relation. This relation you also have to put in the interacting terms, right? So it's not just the spins. You also want to have yeah, maybe I don't understand this equation. So here you have dot products of what? Of
Uh,
vectors, tokens. Uh,
some of uh,
so it's just
mm,
so yeah. I guess I don't understand what that means.
yes, but yes, the
I mean, energy
energy,
will be smallest if all of them are orthogonal, I guess.
but
If this is a
they
dot product.
construct the graphs according to this yes relation.
So it's very easy to have negative. So no, I think I'm lacking understanding of what the energy is. Should be related somehow to the loss function, but here it isn't. So okay, that's fine.
Yes, and okay, and use the relation for critical exponent. They calculate the spatial dimensionality corresponding to the transformer as described in this equation what we have discussed, and they get these values for different size parameters of Qwen model, uh, and how they say uh, the internal dimension and intrinsic dimension at temperature equal 1 are similar.
Mhm.
And it's interesting that they say that these parameters can be higher, yes, but on this, on this, uh, the smaller size and the biggest size, we can see the equal values.
So
And
dimensionality
they,
first grows with the size of the model, and then it jumps down. Okay.
Those two series are uncorrelated, aren't they? I see no correlation
Between what?
between D and D. The internal dimension and the dimension calculated by from alpha.
You see no correlation. I see. Yeah, those are different things, right? So internal dimensions, like when you're trying to embed your graph, and then this D is a critical dimension. You're looking how your energy scales, and then from that you figure out. So I don't think they have to be correlated. So it's a scaling dimension, but yeah, I would want to see clarity in how they are actually calculated.
Okay. Yes, it's some strange results for me too, because they didn't explain why we have equal values of smaller and biggest model size, and
Well, just numerical
this
results, right? So I don't think they're.
yes, and this D and intrinsic D not equal for me, but they say it inverse things.
Mhm.
Okay. And also they have constructed these graphs for another Quen models. For example, Quen coder, Quen mass, according to different size parameters, and
Mhm.
they have obtained the same results. Critical temperature equal 1.2. And they said that the phenomenon holds true across various models. Okay, it looks really same to the first picture.
Mhm.
But okay, let's discuss these graphs. So I have told that they have said that in small models and large models, um, af after temperature more than critical temperature, models have the different behavior, and so they have explained these facts from these graphs. What they did, they uh, they took the graphs between a number of parameters, and so measure of energy in critical temperature and uh, and in infinity temperatures. So they propose to use the difference between the energy at the critical temperature and the energy infinity temperature as an indicator of whether the size of model parameters is large enough. And they find that as the size of the model parameters increases, a higher order phase transition occurs. And they call this phase transition of phase transition. And with small parameter size, the model behaves like a small model. It doesn't recognize the meaninglessness of the text. And with the large parameter size, the model behaves like a large model, and it recognizes the meaninglessness of the text. So, um, and they claim that it will be useful uh, for studying of large language models, and
So let me
and
try to understand. When you have a larger number of parameters, then the difference between the critical energy at critical temperature and energy at infinite temperature becomes smaller. That's what you're trying to say, right? And so at some point
yes,
for a large enough model, at a critical temperature, you already have. But you want your energy to be smaller, no? I mean, this is something I'm confused about. Don't you want in energy to be smaller, or what's a good value for energy for it to produce something meaningful? Is the energy has to be smaller or larger, or it's not related? Yeah.
Um,
So on this graph, so I thought that at small temperature, uh,
yes,
at small temperature, the energy is smaller, and that's when you produce meaningful results. And then at large temperature, you don't produce meaningful results because of this. Yeah, I'm confused. Yeah, there's certainly some kind
so
of phase
yes,
transition happens.
they said if in small models the energy becomes smaller, and it means that uh, this system in the nonsense phase, and uh,
Okay, so you don't want then to, oh, I see. So you want the temperature, the energy temperature depends, you want to be like on the right-hand side, which is similar to the Ising model. Yes? Is that what
yes,
you,
yes,
and the left-hand side is not like Ising model. And you're saying that at some point, as you increase the size of the model, it transitions from how it behaves on the left to how it behaves on the right, something like this. Okay. Okay.
so it's all results from
All
this
right.
work.
Interesting. Let's see. That's all right. Yes.
Yes, yes.
Okay. All right. Let's see if there are any other questions.
Hi, Daria. One of the, I don't know, conclusions out of this paper that I was really surprised about was, regardless of the number of parameters used in a model, it transitioned from being able to provide meaningful responses to meaningless responses, always at the same temperature. What does that mean? How do I use that knowledge to guide me to select the right size of model?
Um, okay. Please repeat your questions.
Yeah, I don't think they answered that question. They just said that, as you increase the size model, at some point, the model will just behave differently um, at larger temperatures.
The description of behaving differently was it will recognize that it's producing nonsense versus not recognizing that it produces nonsense.
Well, I think it will always recognize because you can just study this curve. I mean, I don't know if the model will recognize it, but you can study this curve and see that has the sharp discontinuity going downwards. I mean, that if you can show us this difference between the two models, the two different graphs we had someplace. I think, yeah, there you go. I mean, you can see that it's left graph or right graph by just studying a given model.
Right.
Right.
The first order versus second order phase transition.
That's right. Yeah. So you can do that. But then what they're saying that at some point, as you increase it, it shifts from left to right. So it's a phase transition in the type of phase transitions. So I think that's their claim. I don't know. I don't completely understand. I don't understand what energy is. So for me, it's very hard. It isn't the loss function, something else. And it's probably that quantity that appears in the tension mechanism. But again, why do we want this to be smaller or larger? I mean, I don't know. I'm confused. But the one thing I do agree that this, the study of the phase transitions would probably tell us something interesting about how large language models work. So I don't know. Okay. Other questions, comments? All right, there are no questions. Thanks everyone, and I'll see you next week.